I'm a cognitive archaeologist who studies numbers and early writing systems. Today, I will talk about different ways to represent numbers, 9 different methods used to recognize numbers in prehistory, and what this evidence might suggest about when numbers may have emerged. Let's start with different ways of representing numbers. The forms on the top row represent quantity by instantiating it. That is, they mean 3 in virtue of being 3. And this is true whether they are material objects like fingers, tallies, knots, beads, or counters, or written notations like cuneiform and Roman numerals, and the small numbers 1 through 3 in Chinese and Western numerals. In comparison, the forms on the bottom row represent the sound values of number words in English, Luxembourgish, Korean, and Arabic. These signs mean sounds, and the quantity of their elements is not meaningful as number. In the middle row, single signs represent specific numbers without quantity or sound values. These ciphered signs descend from written numerals, which in turn descend from unwritten precursors like fingers, tallies, and counters. In contrast, phonetic forms descend, albeit indirectly, from the pictures and conventions used in the original writing systems that emerged in Mesopotamia, Egypt, and China. Different ways of representing numbers have different properties that can help us identify numbers in prehistory, and perhaps tell us something about when numbers might have emerged. The 2 categories of signs to the right are from mature writing systems, so they are, by definition, historic rather than prehistoric. We're interested in prehistoric numbers, so we'll start with the ones that are the easiest to identify. These are also the earliest ones that we can identify unambiguously as numbers. We'll also take a look at precursor technologies and why they are more difficult to identify as numbers. The earliest numbers that are unambiguous to our eyes come from Mesopotamia in the mid-4th millennium BCE. They take the form of impressions on bullae and tablets, like the one shown from the city of Susa. These impressions correspond in their shapes and sizes to the proto-cuneiform notations and cuneiform numerals that followed them, and to the numeric counters known as tokens that were their contemporaries and likely predecessors. The numerical meaning of earlier technologies is established through correspondences of shape and size with later technologies, which is the first method that we'll take a look at. This method depends on the presence of later technologies with unambiguous numerical meaning. The method works backwards from the later unambiguous numbers used in complex mathematics to the earlier forms used in bureaucratic accounting. For example, the signs for unit and 10 resemble each other, as do the signs for 3600 and 36,000, while both signs for 600 are combinations of the signs for 60 and 10. Such correspondences are one of several methods that can identify numerical meaning. A second method for identifying numbers involves the value substitution and exchange known as bundling. Instantiation involves element repetition, and bundling replaces a specified amount of that repetition with a convention understood as a consolidated value. For example, in the general counting system in proto-cuneiform, the numerical impressions and the counters known as tokens, 1 small cone meant 1. 10 small cones were bundled and represented by 1 small sphere that meant 10. 6 small spheres were bundled and represented by 1 large cone that meant 6 tens, or 60. The highest number of repetitions without replacement is the unbundled maximum. By reducing repetition, bundling makes numerical information more concise, which makes it more accessible. But of course, the users must learn the conventions that are used for value substitutions. Bundling relations enable us to recognize numbers even in languages that are unknown and scripts that are otherwise untranslated, like Linear A and Elamite. Instantiation and bundling are more apparent in cumulative number systems, like Mesopotamian cuneiform, than in ones with ciphered values, like our familiar Western numerals. In cumulative number systems, instantiation is used to the unbundled maximum. Beyond this point, a bundle is used. For higher values, like those shown in Roman numerals, bundling and instantiation are combined. Cuneiform numerals in this range work in the same way, so 12 is the bundle for 10 and 2 of the signs for 1, just like it was in Roman numerals. Keep in mind that multiple artifacts are needed to analyze bundling. This is because any individual artifact is unlikely to contain the unbundled maximums. For example, here is a clay tablet dated to the 4th millennium BCE. It contains 3 different numerical signs. 2 are unique, while the third is repeated only 4 times, fewer than the unbundled maximum. If this were the only artifact we had, we would be unable to determine the unbundled maximums for any of the signs. In fact, when we have only a single artifact from a particular time period, as is generally the case for periods earlier than 6,000 years ago, it is much more difficult, if not impossible, to reconstruct the number system's organization and structure. A third method of identifying prehistoric numbers involves numerical relations in the form of calculations rather than bundles. Here is a clay tablet from Mesopotamia that calculates geographic area. The tablet was likely a schoolhouse exercise because both sides yield the same answer, even though the numerical amounts differ. Of course, identifying numbers with this method depends on the presence of both calculations and the use of durable recording materials, things that are found only in mature numerical traditions. The earliest unambiguous numbers, the impressions from 6,000 years ago, are associated with numerical counters, frequently known as tokens. Small clay objects were likely used to represent numbers before the practice of impressing them emerged. The question is, how far back in time did this practice go? Small clay objects have been found as early as the 10th millennium BCE. However, the practice of impressing them didn't appear until the 4th millennium BCE, and without the corresponding impressions to preserve the numerical encoding, there are no reliable methods or criteria for diagnosing numerical purpose. Shape and size aren't reliable criteria, since these don't rule out the plausible alternatives, like funerary items, game pieces, children's toys, slingshot pellets, and tool parts. The bottom line is that loose objects don't encode numerical relations, and without numerical encoding, determining whether something was used for counting is very difficult, if not impossible. Before we move on, let's look at how these methods identify numerical meaning in another notational system based on objects. The Inca recorded numerical information with quipu for centuries, perhaps for thousands of years, prior to the Spanish conquest in the 16th century CE. Quipus are devices made of knotted strings. Individual strings contain distinct clusters of knots that represent numbers. The strings preserve the organization of the elements in the same way that the Mesopotamian impressions did for loose counters. Strings are read from the connected top to the loose end, organized as highest number to lowest. On the bottom of the screen, a string is shown from left to right, along with corresponding Roman numerals. While both systems are cumulative, Roman numerals designate value with shape, while quipus use place along the string. Like Roman numerals, quipus involve bundling. Each cluster has between 0 and 9 knots, giving an unbundled maximum of 9. A 10th knot replaces the cluster with a single knot in the next higher place on the string. Although there are no earlier or later technologies known for comparison, quipu can contain calculations and check digits. Quipu are normally interpreted as the same kind of numbers that Western numerals are, a ciphered positional system. Roman numerals, in comparison, are a cumulative additive system. It's a good question which of these two interpretations is correct, as both numerical organizations result in identical knots. However, the Inca were more likely to have had the simpler of the two systems, based on the archaeological premise known as parsimony, which says that the simplest explanation that fits the known facts is likely to be the correct one. So Inca numbers were more likely to have been like Roman numerals than Western ones. Prehistoric bones incised with notches may look like tallies to our eyes, but unfortunately, resemblance is not a reliable criterion. These devices also tend to be isolated in time and space, so methods that require multiple artifacts cannot be used with them. Accordingly, the fourth method looks at the surface disposition and morphological characteristics of the marks. In the one shown on the screen, the marks are regular in their length and spacing, so they do not encode relations of any kind, including numerical. Surface gloss suggests that this piece of bone was curated for a long time, implying a long-term purpose. That kind of suggests that the purpose wasn't numerical because numbers tend to be used and then discarded. In other words, we write down a number like 30, and then as soon as we've used that number, we don't need that representation anymore. We don't keep it for long periods of time to enshrine it in some way. So this suggests that we consider how the artifact would have been used. It probably wasn't used as a calendar because there aren't any indications of the marks being incremented with twine or coloration. Its size is also very significant. This artifact is just 3 inches long, about the length of an adult index finger, so the marks on it are even smaller. Very small marks are difficult to count, and this implies, as well as the other characteristics, that they were unlikely to have meant numbers. So our fifth method tries to match the total quantity of marks to some known phenomenon, like the number of nights in a lunar cycle. So whenever we find an article that has between 28 to 32 notches, like this one does, it's assumed that it may have meant the lunar cycle. And perhaps it did. However, as I just noted, there is no indication that the notches were incremented in the fashion of a calendar. Furthermore, in contemporary systems, around 30 marks can mean all of a category rather than the specific number. The sixth method considers contemporary examples like this Australian message stick from the early 20th century. It too is very small. Now, these notches serve a mnemonic purpose rather than indicating numbers. The message on this artifact consents to a marriage on the condition that the prospective bridegroom builds a residence for the newlyweds, and that the newlyweds provide the brother of the bride with specific goods. The problem with this method is threefold. First, there hasn't yet been a systematic cross-cultural study of such artifacts that includes the associated number systems. Second, a systematic study will be difficult because such artifacts are poorly documented in the ethnographic literature. Finally, and most importantly, the meaning of such marks can vary widely between societies, so what they mean to one may have no bearing on what they mean to another. On the other hand, where we do have cultural insight, it warns us that marks may not be numbers, and that there might not be any correlation between the number of notches and the number system of the society who made the artifact. For example, many Australian societies count no higher than 3 or 10, but message sticks can contain upwards of 30 notches, and without meaning 30 of something, and without meaning the lunar cycle. The seventh method examines prehistoric marks microscopically and compares them to experimental marks to determine whether the same or different tools were used in making them. The same tool is assumed to mean that marks were accumulated in a single session, indicating a purpose like decoration. Different tools, on the other hand, are assumed to mean that marks were accumulated over multiple sessions, perhaps for a purpose like counting. However, it certainly seems possible to use the same tool for accumulating and different tools for making decorative marks, and no one has yet compared this assumption to actual cross-cultural practices. Importantly, the premise itself becomes questionable when the marks produced are indistinguishable except under the microscope, since visual indistinguishability shows overdetermination. That is, whoever made the marks invested more time in producing regularity of form than counting might typically warrant. It's one thing to accumulate marks for the purpose of counting things, and it's another thing to make marks that look like one another in their shape, size, and spacing. One of the things we do know from contemporary number systems is that counting begins on the hands, and this is why so many number systems around the world are patterned by quantities like 10, 5, and 20. 20, of course, means you're including the toes. Gestures like finger counting are archaeologically invisible, with one possible exception: the negative hand stencils found in 2 caves in France. From all 5 fingers extended to all 5 fingers bent, the human hand can make 32 different patterns of long and short fingers. At Kosker Cave, only 5 of these patterns are found, and they are the ones that look like typical finger counting. Gargus, a nearby site, has 10 combinations, the 5 that look like finger counting, and another 5 thought to have been hunting signs. These patterns, 5 or 10 of the 32 possible, are statistically interesting, which is our 8th method. The patterns are not randomly distributed throughout the 32 possible, and the specific fingers used are inconsistent with alternative explanations like accidents, disease, and ritual mutilation. These factors, in turn, suggest that numbers are a likely explanation. However, statistical likelihood doesn't mean that something actually happened. Another example of statistical likelihood comes from Ishengo in the Democratic Republic of the Congo. This inscribed bone is about 25,000 years old. It has 3 rows of marks that are separated into groups by wider spacing. The first row of marks contains the prime numbers between 10 and 20. The second row contains the results of 10 and 20 plus and minus 1. The third row consists of marks that suggest halving and doubling, but not consistently. The idea that such groupings could be produced accidentally is highly improbable. That said, it's nonetheless difficult to reconcile the complex mathematical concepts suggested by the marks with the use of rudimentary encoding, spacing, but not bundling. We also ignore the differences in lengths to come up with these quantities, because if you factor in the differences in lengths, then the numbers become much less interesting mathematically. The artifact also has a piece of quartz affixed to one end, so it was likely used for engraving, something that doesn't easily fit with a numerical purpose. So again, we are left with tantalizing hints of numbers before the mid-4th millennium BCE, but no conclusive evidence of it. The 9th and final method looks for wear marks and other characteristics that might indicate how an object was used. Some of the earliest beads known are from Blombos Cave in South Africa. These are shells with punctures, wear marks indicating they were strung, and traces of ochre, a mineral that is often used as body paint. While the strings themselves have long since perished, these characteristics suggest that the beads were worn as a necklace. Beads were widely prevalent in Africa, found in at least 30 sites over 4,000 miles and more than 40,000 years. However, while many societies make and wear beads, few count with them, and there are no methods or criteria for distinguishing ornamental from numerical use. So, while wear patterns can show that beads were strung, they cannot determine whether they were also used for counting. Beads also cannot provide insight into the associated number system. Strung beads can be used like a rosary, a kind of counting that does not involve numbers, whether or not numbers are available. Beads can also be strung and counted into the tens of thousands, as we will see on the next slide. A recent example of counting beads into the tens of thousands comes from California. Pomo beads, known as wampum, were used throughout the region as a medium of exchange. While beads, bead blanks, and specialized drills have been found in Pomo sites dated to the last 500 years, the practice of counting beads is archaeologically invisible. What we know about Pomo bead counting comes from observations of language and behaviors, the kinds of data unavailable for prehistoric peoples. Some Upper Paleolithic societies made beads by the tens of thousands. For example, about 30,000 years ago in Russia, 3 people were buried with over 13,000 beads of mammoth ivory. Each bead took about 45 minutes to make, so the total represents at least 10,000 hours of labor. This social investment suggests that beads were valuable and thus likely to have been counted. However, there currently aren't any methods for determining this. It would be nice if labor investment and wealth told us something about prehistoric numbers. However, social conditions don't mean numbers or counting, only that the factors that motivate their development were present. Here are some of the best-known artifacts thought perhaps to represent prehistoric counting in Europe, the Near East, and Africa. They have been plotted on a logarithmic timescale. Remember that record keeping that incorporates bundling and durable materials emerges under conditions of demographic increase and contact associated with the Neolithic. Most of these artifacts are incised bones, but there are also strung beads and hand stencils, and the first unambiguous numbers and the associated loose counters. In all, we have discussed 9 methods for identifying prehistoric numbers and their important constraints. Many of them suggest that numbers most likely emerged during the Upper Paleolithic, but none of them, unfortunately, establish this conclusively. The earliest unambiguous numbers remain the numerical impressions from Mesopotamia. Thanks very much for listening to this talk.